All right, so today we're going to look at Chapter 2 Big Concepts, number 4 and 5, Graphing Piecewise Defined Functions and Absolute Value Functions. Our learning targets today, I am learning to graph and analyze piecewise defined functions. I'm learning to graph and analyze absolute value functions. So a piecewise defined function is written using two or more pieces of expressions. When graphing a piecewise defined function, you'll have solid dots and open dots. And this means if it's a solid dot that you include the point on your graph. However, if it's an open, you do not include. The point on the graph. All right, so let's take a look at our first examples. It says graph and identify the domain and range of the function f of x equals x minus 2 when x is less than -1 and x plus 3 when x is greater than or equal to -1. So we want to look at each piece separately. So the first piece we're going to look at is x minus 2 for x less than -1. Now the key here is this x less than -1. That means when x is at the -1, we're going to have a barrier. And I'm going ahead to draw this dotted little barrier and I'll erase it later. And this says, hey, go ahead and graph the function x minus 2, but for all values greater than -1, erase it and keep all the values less than -1. So when we take a look at this graph, we have a y-intercept of -2. So we'll go ahead and plot that. But then we have a slope of 1. So up 1 over 1, up 1 over 1, down 1 over 1. All right, so I've hit my barrier. Now, because this is a less than sign, I'm going to have an open circle. And then I'm going to go on. Down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. And now I'm only going to graph the portion of my graph that starts at this -1 value and goes down. Once I've drawn that graph, I can erase all the values that I had plotted that were greater than this -1. Now, when we look at this next function of x plus 3 for greater than or equal to -1, I'll go to that -1 barrier again. This is where I cannot cross. So I'll go to 3 because that is my y-intercept. Up 1 over 1, down 1 over 1, and I've hit my barrier. Now, this one's going to be a closed circle because it's greater than or equal to. And now I'm going to draw my graph for all values greater than or equal to -1. Once I've drawn the x plus 3 function for all values x greater than or equal to -1, I am going to go ahead and erase that barrier line. That just helped me determine what parts of my graph that needed to be plotted. And this is our graph of the function f of x equals x minus 2 for x less than -1 and x plus 3 for x greater than -1. However, the question also asks to identify the domain and range. So let's take a look at our domain. The domain refers to all possible x values. And if we look along this x-axis, we have values represented by every value of this graph. So if it's -6, we're down here at -8. If it's +2, we're up here at 5. But what happens if it's -1? Which value does x represent? Or what value does it yield? It yields the +2. So yes, even though we have this jump in our function, it still accounts for that range. So we have all values. That's all real numbers. So in interval notation, we have -∞ to +∞. And then let's take a look at our range. This is where it gets a little trickier because there is this jump in our graph. So we need to make sure that we do not include the values in between the two pieces. From this side, we see that our arrow is decreasing down. So our range goes from -infinity, and then it keeps going, and then it stops at the value -3. Now, this is a parenthesis. We end with a parenthesis because this is an open circle. And then we're going to union this part of the graph with this part of the graph. And it continues at the value of 2. This time we use a bracket because we are allowed to include that 2 value. And then we go to +infinity. And that's our range. All right, let's go ahead and work backwards. This time the graph is given to us and we have to write the function. And so we need to look at the 3 separate pieces. So let's take a look at piece 1, which I just highlighted in green. So piece 1 is a linear function, so we know it's going to take the form of y equals mx plus b. Well, let's first find our y-intercept. Well, here it is. It's at 3, so that's +3. And if we find our slope, we go up 2 over 1. So we know that the green portion is 2x plus 3. So I'll go f of x equals curly brace 2x plus 3 for values. Now let's take a look. This is an open circle, and we are decreasing going to the left, which means I want values that are less than, so I'll use the less than symbol, and it looks like we're at 1 on our x-axis, and so I'll put 1. All right, so now let's look at our second piece. Boom, here it is. So if we take a look at this second piece of our graph, it is also a linear function. And if we were to continue to draw this linear function, we would see that it has a y-intercept of 2. So we know it's y equals something x plus 2. And let's take a look at our slope. We go down 1 to the right 1. So down 1, right 1 is -1 over 1, which equals -1. So here we have -1x squared, x plus 2. So now we'll come over here, and our next piece is -x plus 2, comma. And notice, there are 2 pieces here. We have our starting and our ending. Our starting value is at 1. So we'll have 1 is less than our x value, and our ending part is at 2. So we want all the pieces in between 1 and 2. And once again, they are less than symbols because we want all the values between 1 and 2. All right, now we have one more piece. This is a constant function, and constant functions are horizontal lines, and we just have to see where this value is. So it's at 1, 2, 3, and so our value is 3. And that is for functions that are greater than 2, because here's our 2 on our x-axis and it lines up perfectly. Now notice all of these were open circles, so all of our symbols were inequalities that were less than or greater than. Just for giggles, let's take a look at our domain. Do we have all x values represented? No, we don't. If you notice, we have open circles here. I'll go ahead and highlight them. So we have open circles here on this line, and open circles here on this line, which means that our graph does not include those values. So when we take a look at that domain in interval notation, we're going to have to use unions. So we're going from negative infinity all the way up to 2. We can't include 2 because it's an open circle. And then we start back at 2, once again not including it, going to 3. And we don't include that again. And then we start at 3 and go to infinity. Now our range is a little different as well. Notice it is ever decreasing into that negative y value. However, when we look, what is the highest y value represented here? It's 5, and we can't touch it. So it's negative infinity to 5. All right, so the next part we're going to talk about is those piecewise defined functions. A common type of piecewise defined function is called the step function, or otherwise known as the greatest integer function. And that's just a function that consists of line segments. So here is a step function. It kind of looks like a staircase. And the symbol here means the greatest integer. We call that a double bar. So the greatest integer of x means the greatest integer less than or equal to x. The key here is less than or equal. So if I were to just give you some examples, if we had 3.25, what integer is less than or equal to x? Well, in this case, because it's less than or equal, we have to round down to the nearest integer. So in this case, the answer is 3. But if we had an integer of, let's say, negative 4.6, once again, we have to round down to less than or equal. And pay attention, this is a negative. So we have to go to the left even further to negative 5. What about 2.9? If you said 2, that's awesome because that is absolutely correct. And then we have negative 1.3, which rounds down to negative 2. And then let's try one more. What if we had a positive number? What would that round down to? It would stay the same at 6. All right, so let's take a look at an example of the greatest integer function. All right, so it says an automotive repair center charges $50 for any part of the first hour of labor and $35 for any part of each additional hour. Draw a graph that represents the situation. So before we can even draw our graph, let's take a look at what we're looking at. X is going to refer to the time we have, and Y is going to refer to the cost. How much am I having to pay out in labor? So let's go ahead and let's make a quick little chart. Here we have our X, here we have our Y. Now, it says the auto repair center charges $50 for any part of that first hour. So it doesn't matter if I'm there for 1 minute or 59 minutes, it's still going to cost the same part, same amount. So from 0 less than X less than 60. Notice I'm using less thans because I can get as close to as I can to 60 and I can get as close as I can to 0. I just can't touch them. It's going to cost me $50. All right. But then I get into that next hour. All right. So instead of going by minutes, let's actually go by hours. So between hour 0 and hour 1, it's $50. So what happens after we pass that 1 hour mark? How much does it cost between the first and second hour? Well, it says, and $35 for each additional hour. And it's any part of the hour. So it doesn't matter if it's 15 minutes over, 30 minutes over, 57 minutes over. It's each additional part. So now I add 35 to my cost and it becomes $85. All right, so if I hit that 2 hour mark, and then go to 3, so I'm including 2, I include the 2 because at 2 hours, I have to pay an additional $35. So then I get to 120. So that one is less than or equal to because I have to include the 2. And then let's say I actually hit the 3-hour mark. What do we get to? We get to 155. Oh man, I don't know what's happening, but they have to keep working on my car. I hit the 4-hour mark. Hopefully, I'll be out of there before we hit the 5-hour mark. And so we have to add an additional $35, and that gets us a total cost of $190. So this is how a step function works in real life. So we go to 0, and we can include 0. So at 0, we're at 50. And then for any part of that additional hour, we go across, and we go all the way to the hour mark, except we cannot put a solid dot on 1, because once we hit that 1 hour mark, it goes up to the next value of 85. So here I'll go to 85. I hit my 1 hour mark. I'm going along. Oh, now I'm at the 2 hour mark. I have to do an open circle because once I hit 2 hours, I go to 120. So here's the 120. I go across. He's taking more and more labor. I'm at the 3-hour mark, except once I hit the 3-hour mark, I have to go up even further to $155. I just keep shelling out the cash. I keep going to the 4-hour mark. But once I hit the 4-hour mark, I'm all the way back up to 190. And so on and so forth. So this is how that step function would be represented or graphed in the real world. All right, let's take a look at absolute value. Absolute value is a concept that you learned in 8th grade and probably even Algebra 1. However, we're going to take a look at it on a deeper aspect. So the absolute value function is represented as f of x equals the absolute value of x, where these two bars are straight up and down. All right, so let's go ahead and make a chart. X and f of x. The biggest thing here is about absolute value is that any input for x, once simplified, becomes positive because it's in these absolute value bars. It's actually measuring the distance from 0, and since distance has to always be positive, even if there's a negative number in here, it'll yield a positive output. So let's take a look at the 5 values that we most always use when graphing: -2, -1, 0, 1, and 2. So if I put a -2 in for the absolute value for x, I get the absolute value of -2 is a +2. And then if I put in a -1, the absolute value of -1 is a +1. The absolute value of 0 is 0. The absolute value of 1 is 1. And the absolute value of 2 is 2. So if I go to plot these, I get a very distinct V-shaped graph. So we have a very, very distinct V-shaped graph. So under type of graph, we're going to put V-shape. All right, so let's take a look at our domain. Our domain is our x values. Well, we're going off forever in the left direction. We're going off forever in the right direction. So our domain is actually all real numbers, which is -infinity to infinity. Now our range, we're going up forever in the positive value, but look at our smallest y value is 0. So our range actually starts at 0, and we can include the value 0. It goes to 0 to infinity. Intercepts. I only have one intercept, and that is at 0, 0. And if you notice, it doesn't go below this. This parent function does not go below our x-axis. So that means it is not defined for values of f of x that are less than 0. All right, so one last example. Let's go ahead and plot the following graph and then find the domain and range. So we're going to make a table of values. All right, on one side of my table, I have x, and on the other side, I have f of x. So let's use our 5 values: -2, -1, 0, 1, and 2. And let's go ahead and simplify these out. So we have the absolute value of 2 times negative 2 minus 4. That gives us the absolute value of negative 4 minus 4, which gives us 4 minus 4, which equals 0. So our first point is negative 2, 0. So I'm going to go over here and plot negative 2, 0. All right, let's do it for negative 1. So 2 times negative 1 minus 4 gets us negative 2 minus 4, the absolute value of negative 2 minus 4, which gets us 2 minus 4, which gets us negative 2. So here we have negative 1, negative 2. So now we get 2 times 0 minus 4, which is the absolute value of 0 minus 4, which is 0 minus 4, which is negative 4. So next point, 0, negative 4. And now we're going to go on to the number 1. 2 times 1 minus 4, which is the absolute value of 2 minus 4, which is 2 minus 4, which is negative 2. So now we have 1, negative 2. And then if we follow the same pattern, 2 times 2, the absolute value of 2 times 2 minus 4 yields us the absolute value of 4 minus 4, which gets us a value of 0. So now we have 2, 0. Now let's connect our points and draw that very distinct V-shaped graph. All right, so we drew our V-shaped graph, and so now let's find our domain. All our possible x values. If you take a look, we're increasing all the way to the left, and we keep on increasing all the way to the right. So our domain is negative infinity to infinity. We have values on going in either direction forever. Now our range actually starts at negative 4 because we have no other values less than negative 4. But we can include the value of negative 4, so we go negative 4 with a bracket, and then it continues on and on forever, so we get a positive infinity. All right, so that was big concepts numbers 4 and 5. If you have any questions, let me know.